Okay, so let's continue with lecture 2, which will be completely independent from lecture 1. So today it's just random walks. And we will study centered, downward, skip-free, integer valued random walks in the domain of attraction of maybe I won't go there. Stable. Okay, one shock is one line.
So much for centering.
Okay, so what do I mean by this? I will take Sn to be x1 plus xn with the xi's, the jumps of the random walk, IID, such that three assumptions. One, on Z, we work with integer jumps. The walk is downward skip free. When it goes down by a jump of size 1 at most. To avoid degenerate cases, I assume that I can have positive jumps. 2, the walk is centered. So this is one of the reasons I write Sn and not Wn, because tomorrow we will work with subcritical trees, and the associated walk will have a negative drift. So to use the results of today, we will add to the walk with negative drift a positive drift, so that we will be in position to use these results. And 3, x1 is in the domain of attraction of the domain of attraction of an alpha stable law, and I will explain what this means, with alpha greater than 1 and at most equal to 2. So 3 is an extension of x1 has finite variance. Essentially 3 means we have a central limit theorem for Sn, but potentially x1 can have infinite variance. So 3 means either the variance of x1 is finite and alpha equal to 2. This is the standard central limit case, central limit theorem case, or the tail of x1 is of the form L of x divided by x to the power alpha. So the tail of x1 is heavy with L slowly varying. And we already saw at the end of lecture 1 what slowly varying is. It means that L of ux divided by L of x goes to 1 as x goes to infinity for every positive u which is fixed. And for example, L of x can be equal to log x 1 over log x, or L of x can be asymptotic to some constant. So if you do not like slowly varying functions yet, you can replace this by equivalent to some constant over x to the power alpha. Okay? 3 also means if you look at the truncated second moment, then it is of the form slowly varying function u to the power 2 minus alpha with L0 slowly varying. This is a bit more useful to put together the case alpha equal to finite variance, infinite variance. So it's, for technical reasons, a bit simpler to work with L0 instead of L. But anyway. Okay, so 3 also means that there exists a sequence Bn of scaling constants such that Sn divided by Bn converges in distribution to some random variable y whose Laplace transform is explicit, which is lambda to the alpha. And for alpha equal to, this is y is a multiple of a standard Gaussian random variable. So alpha equal to 2, essentially, it's just the central limit theorem. But in 3, we're allowed to have infinite variance. And this tells us that if we have this regularity assumption on the tail, we get a central limit theorem. And the limit is not a Gaussian distribution anymore, but an alpha stable, spectrally positive random variable. Spectrally positive because I have this condition, I do not make very large negative jumps. And this is the most general condition you can have. You can show that if you want something like that to hold, then you are forced to have a regularity condition on the tail. So this is the most general assumptions you can make if you want to have a central limit theorem like this. So are there any questions on this?
Igor, why alpha not bigger than 2?
So what you can do is here, you say, okay, I take here alpha equal to 10.
Okay.
But then by definition, x1 will be in the domain of attraction of a stable law of index 2, because you are in the domain of attraction of a Gaussian distribution because you have finite variance. So yeah, so this is, yeah. So if you have, so yeah, maybe example. If probability that x is equal to n is, let's say, L of n divided by n to the power 1 plus beta, or, okay, let's write it like that, with beta greater than 2, x is in the domain of attraction of a two-stable random variable. Because x has finite variance. Okay, so we need to take alpha greater than 1 because we want to have a first moment. And if you want to have a first moment, this thing should be summable. And essentially, for this reason, we take alpha greater than 1. And to, okay, maybe a last remark before saying something about the asymptotic behavior of slowly varying functions is that the scaling constants Bn can be chosen more or less explicitly. We can take Bn such that n L0 of Bn divided by Bn to the power alpha goes to some constant. And if I want to have this expression, it should be something like that, where gamma is the gamma function. And this is interpreted as being equal to 2 for alpha equal to 2. This is actually continuous around alpha equal to 2. So the scaling constants can be chosen more or less explicitly if you know L0. So in particular, if the variance of x1 is finite, you take Bn of order square root n. So this is the central limit theorem. If the tail behaves like some constant over x to the alpha with alpha between 1 and 2, then Bn is asymptotic to some other constant n to the power 1 over alpha. So again, if you do not like slowly varying functions yet, you can replace slowly varying functions by constants. And then the scaling Bn to have the central limit theorem is not of order square root anymore, but n to the power 1 over alpha. And if you add slowly varying functions, you have to have slowly varying corrections. Okay, are there any questions on this? And often in the asymptotic estimates, you can get rid of slowly varying functions because they are slowly varying. Useful estimate, which comes from a general representation result for slowly varying function, which are called Potter bounds. So for every positive alpha, I have to make the quantifiers right. Yeah. There exists M such that xy sufficiently large implies L of x over L of y less than the constant maximum between x over y to the power delta, x over y to the power minus delta. In the case where L goes to infinity, this says that L goes to infinity slower than any polynomial. L does not cannot go to infinity too large. If you think of L of being the function logarithm, indeed the log x is a little o of x to the power delta around infinity. Okay. So here I will just put the main things we will need. So we will need this. Okay. We will need this. Here, so some constant depending on alpha, which is not that important. Okay. And at the end of the lecture, our goal will be to show that if you take this random walk Sn and you condition it to be large at time n, large with respect to n, so at least of order epsilon n, then there is a one big jump principle. You will have one big jump of order n, and once you remove this big jump, actually all the other jumps are IID. So it's a very strong result. But to arrive to that, we need some estimates. First, a maximal inequality. Which has something to do with the maximum of the n first jumps. And it says the following. I think such maximal inequalities were first obtained by Nagaev. And I guess the most general treatment in the most general case is by Denisov, Dicker, Schneer. And this is in this paper, it's very, very general, so it's a good reference to have in mind. And the result says that there exists a constant such that for every, so it's a uniform estimate, such that the probability that at time n you are above a certain level, here I put Bn okay, I could put just x, but I put Bn to philosophically keep in mind that Sn is of order Bn, thanks to this result. Okay, and now I look at the probability that I go above a certain level, but that the maximal jump is not too large. I have to, okay, maybe it's greater than or equal to. Okay, we'll see. Anyway, C Bn. This is less than or equal to C e to the power minus x over C. It says that you cannot, if the Sn is very large, Mn has to be, roughly speaking, of the same order of Sn unless you pay an exponential cost. Okay, are there any questions on the statement? So the proof is rather short, a bit tricky, but I think it's a general idea which can be useful in other contexts. The idea is to use a truncation argument and to introduce a truncated random walk. So this is, I think, the idea of Nagaev. S tilde n, which is the same random walk, but you keep only the jumps which do not exceed CBN. And so that the probability we're interested in let's put greater than or equal to, less than or equal to. This probability we're interested in is just less than or equal to the probability that this truncated random walk goes above level xbn. So this is the main idea. Indeed, this event is included in this event. So the advantage is now we have just an estimate on a random walk, but the price to pay is that the increments of the random walk now depend on n. But we will still be able to manipulate this by using an exponential inequality. This we write it as the probability that the exponential of some lambda n, which we will choose s tilde n, is greater than or equal to e to the lambda n xbn, with lambda n a constant we will choose just in a moment. And this is less than or equal to e to the minus x lambda n bn. So the jump distribution of s tilde depends on n, but the jumps are still independent, so I get this. Now, in view of the result, I take lambda n to be 1 over cbn. And so I see that this is e to the minus x over c. Which is this. And then I have something here. And the goal is to show that this is of order 1. This can be bounded from above by a constant. And now the idea to manipulate this term is to write So lambda n the idea is to, so usually you can say, okay, I use the Taylor expansion and so on, but here the idea is to write explicitly it like this. A first order term, something which is of the sort of first order and something of the second order with Mn, which is, I'll try to not mix things up. Okay, so this is the first order term, and Sn will be the second order term, which will just be okay, minus S tilde 1 over Cbn minus 1. So the idea is to force 1 and first moment to appear, and then we just compensate in Sn. And now we show that Mn is a big O of 1 over n, and Sn is a big O of 1 over n, and with which will suffice by taking by transforming this with the exponential and a logarithm. So for Mn, we look at what is Mn. S tilde is a truncated random walk. So this is just 1 over Cbn, expectation of x1, indicator x1 is less than or equal to Cbn. And now the idea is to use the fact that x1 is centered. So we can replace this by 1 over Cbn, expectation of x1, indicator x1 is greater than Cbn. Because this plus this is equal to the expectation of x1, which is 0. And this is good because we have control essentially on tails of x1. We have controls on here on the truncated moment of order 2. And more generally, we can get controls of all truncated moments of any order. So this is something, once you get truncated moments of x1, you are in good shape because you can use known estimates. So here it is possible to show that that if you look at the truncated moment like this, try to, okay, it's like that. You have this estimate. This goes to 0 when n goes to infinity at a speed which is of order 1 over n to the power alpha minus 1 with a slowly varying correction, and more precisely you have this estimate. Where does this come from? If you assume, for example, this, if you assume a stronger asymptotic estimate like this without any slowly varying functions, then it's very easy to write this expectation as a sum and to integrate the tail and so on. So I hope this is not that mysterious. Okay, and this gives Mn big O of 1 over n. Okay, because this 1 over n will give you n to the power alpha, and then you just use this to conclude. So I don't want to enter technical details. Again, everything is detailed in the lecture notes, but I hope that this is clear. And now for Sn, so the idea is that S tilde 1 cannot be too large. It is at most CBN. So here you have something which is bounded. Here you have something which is bounded. And so to force a second moment to appear, the idea is to divide this quantity by S tilde 1 over CBN squared. So write divided by S tilde 1 over CBN square, and then you just add it again here. And this is less than a constant because S tilde 1 over CBN is bounded. So around 0 it is bounded, and you do not go too high, so this is bounded as well. So you see that Sn is a big O of the expectation of S tilde 1 squared divided by Bn squared. And this is a big O of what is S tilde 1? It's the expectation of x1 square, indicator x1 less than or equal to CBN, divided by Bn squared. And this truncated second moment is here. So you replace, and you see that this is a big O of 1 over n. Just by using this and this. So the proof may seem maybe a little technical, but okay, there are essentially two ideas. First, introduce a truncated random walk, use an exponential inequality, and force the appearance of two terms and control them. So here the proof is rather short. You can look at the Denisov Dicker-Schneer paper. The proof is a bit longer in a more general context, but the idea is really the same. So I wanted here to present it in this maybe less general context, but still to convey the main ideas. Are there questions on this? Okay, so maybe I write the exponential inequality here. So now we will show a local estimate. We will condition Sn on being very large. We'll condition Sn to be of order, let's say, n. And so we will need to estimate the probability of this event on which we are conditioning. And for local estimates, very often you need more regularity, local regularity. So here we assume, in addition, that not only we have the tail which is regularly varying, but here really the distribution with beta greater than 1, and set alpha to be the minimum between 2 and beta for the reason we saw before. In particular, if x1 has finite variance, you cannot always apply what follows. Even when x1 has finite variance, you have to have a sort of polynomial decay. So this is rather restrictive. But it is under this condition that we will have this one big jump principle. Theorem. Due to Rondoni, fix positive epsilon uniformly for m at least epsilon n, the probability that at time n we are very high is asymptotic as n goes to infinity to n probability that x1 is equal to m. So intuitively speaking, this means that saying that at time n we are in M, it's saying that one of the n jumps is M. So this is intuitively a sort of one big jump principle, but here only stated with probabilities, not with trajectories. But we'll see that the first step to get a one big jump principle for trajectories is to first get it for probabilities, and then we will use this to get a more precise result for trajectories. And there has been a lot of work concerning this one big jump domain. Okay, here epsilon n, can you go below epsilon n? What is the lowest thing you can put here so that this holds? So these are important questions, and I think the most thorough treatment is in this Denisov-Dicker-Schneer paper, who show that actually you can go to n to some power, which is below, but this will suffice for our application for random trees. I will not give the whole proof, which is detailed in the lecture notes, but I will give maybe just the idea, which uses this maximal inequality. And Denisov-Dicker-Schneer also really use this maximal inequality. So the idea is to show this by progressively adding new information here. By adding information of the form, the maximal jump is at least something. At time n minus 1, I am in this interval, and so on. So the idea is to show this estimate with more information here. The idea being this information you add when it is not verified, it is a little o of this. Okay, so okay, I'm not clear. Okay, we'll see what happens in the proof. So the idea is to write probability of Sn equal to m as the sum of 3 terms. And before that, there is a cutoff. We fix L sub m to be log m over log m cube. So what is P1? P1 is the probability that we have a big jump, which is at least Lm. Our goal is to show that it is of order m, but here we lose just a factor log. And this probability is that there is a unique big jump. So xn Lm. And the maximum of the first n jumps is less than. And here we have a factor n because by exchangeability you could have the biggest jump greater than Lm and the others less than Lm. here I put n, but you can do the same for n minus 1, n minus 2, and so on. And all the events are disjoint. Okay. So P1 is saying at time n we have a one big jump at least equal to Lm, and all the other jumps are smaller. Okay. Now P2 is, well, all the jumps are smaller than Lm. And what is P3? We have at least two jumps which are greater than or equal to Lm. And the idea is to show that P2 and P3 are a little o of this quantity, and that the main contribution comes from P1. And on P1, the probability of P1 will be this. So let's first look P2. Here the idea is to use this exponential inequality by bounding this by the probability that Sn is at most m, Mn is less than or equal to Lm. So by the exponential inequality here, I get that this is minus log m cubed. Okay, and this you can check that this is a little o of n L of m over m to the power 1 plus beta. Because this exponential term kills these polynomial terms. And here we use the fact that the slowly varying function at infinity cannot grow faster than any polynomial. Okay, so
The L actually is strictly positive. Here.
sorry.
So the L in your assumption, right, is a slowly varying function. But it
Yes.
should be also strictly
Yes,
positive.
yes, thank. Yes, thank you. Yeah, I guess to define the limits, if you want this to be defined when x goes to infinity, implicitly you assume that the denominator is well defined for x sufficiently large. But yeah, I should have mentioned it, thanks. Okay, so now P3. P3, you have two jumps, at least two jumps greater than Lm. So you bound this by n squared, probability that Sn is equal to m. And let's say the first jump is at most Lm, and the second jump is at most Lm. And here you can bound it. Here I'm skipping a bit the details, but you can bound it by the probability that x1 is greater than or equal to Lm, and then a local probability that x1 is equal to something. So here I'm going a bit fast, but okay, here you have x1 is at least Lm, okay, but here you have a local probability Sn has to be equal to something, which means that x2 has to be equal to something, m minus the other things. So you have the probability that x2 is equal to something, and this something is at least Lm. So you have this bound, and this is not very difficult then to show that again this is a little o of n why? So you have this term, this n cancels this. The orange term is the same order than this. And so the desired result just comes from the fact that this goes to infinity, to 0. Why? Because this is of order n to Lm to the power beta, and beta is greater than 1. Okay, Lm is of order m. M is greater than n. Beta is greater than 1, so all this thing goes to 0. Okay, so sorry it's a bit technical, but just want to give the main ideas of this estimate. Again, here the idea is to separate the probabilities in different probabilities depending on where the largest jump is, how many large jumps we have. And again, I think this is, this appears in various contexts. Yes?
If you turn the equal to m in this asymptotic into larger than m, can you remove the assumption that you...
Yes, exactly. This was actually Nagaev's result. Nagaev showed that if you assume the assumptions of the 1, so if you assume just this, if you assume this, then this holds like that. And actually, Dornier adapted a bit the proof of Nagaev. But the proof of Nagaev of this under this weaker assumption follows the same lines. But at that time, this maximal inequality in this simple form was not there yet, so it was in a bit more complicated form, but essentially the ideas are the same.
And this also works for beta larger than 2?
Yes, yes, yes. Are there other questions on this? And so the difficult part is P1. So here I just will give you the idea to estimate P1. The idea is to separate according to 3 cases. First case, Sn minus 1 is large. Let's say larger than m over log m. This will happen with very low probability, because if Sn is very large and Mn minus 1 is not that large, this gives an exponential cost by this. 2, Sn minus 1 is very small. Let's say smaller than minus n to some power. Okay, this happens with probability tending to 0. And when this happens, to have Sn equal to m, you must have the last jump, which is very large. And so you see that everything, so this gives you a asymptotic small contribution. And 3, this is where the probability is concentrated, is when Sn minus 1 is in this interval. And then it is not by looking on this expression, you cut this probability into 2. You will have a product of 2 terms. The first term depends only on Sn minus 1. It tells you that Sn minus 1 is in this interval, and the maximum of the first n minus 1 jumps is at most Lm. Okay, this will be the first probability. And the second probability is xn does something which brings s minus 1 from this interval to m at time n. And this will give you exactly something which is of order, something of this order. It will not be m, it will be m plus or minus something which is here, but the something which is here is much smaller than m. So this is what makes everything work. So sorry, it's rather technical, but anyway, I just wanted to show you the main ideas. Other questions on this?
Sorry.
Yes.
Going back to the maximal inequality, if I try to apply it to something that converges to Brownian motion, it seems like there's some kind of contradiction. So if your Bn is of the order square root n, your maximal inequality tells you that the maximal jump is of the order of the displacement.
It tells you. Yeah, you're right. What does this? So the question is, if you assume that everything has finite variance, Bn is of order square root n. And we know.
I think it
Or-
holds true if you have to rule out the beta equal 1 case for this.
But here, you take beta equal 10, or so I should check.
Yeah, this is true in the heavy-tailed case, right? That the sum is like the maximum.
Yeah, it tells you that the
But-
stable process has jumps.
Yeah, but the question is in the Brownian
In the
case.
Brownian
Yes,
case,
when you have a heavy
not,
tail, when you have a heavy tail, but you have finite variance. Yes, okay. I will check it and I'll, it's,
Anyway,
it's,
a wider question is that this is something that is not really what we want to look at when we want to look at concentration, because here you don't ask the random walk to do extraordinary things. Bn is the usual.
yes, Bn is the, Here Bn is a natural scale, it's the scale on which Sn lives. Okay, so I'll check it and I'll tell tomorrow, there's something weird, sorry for that. Because we know that Bn equal 10. Yeah, so I'll have to check. Maybe the problem comes from the fact that instead of taking here, you should maybe put not Bn, but this the same thing with the beta, not the alpha. I don't know. Okay, I'll check and I'll tomorrow. Yeah, sorry. Are there other questions?
I think actually this theorem by Doney, right? There you have also to assume that because otherwise, if you take m is epsilon times n,
Yes.
and the Sn is something like standard Gaussian, like the xi's are standard Gaussian,
Yes.
then the two sides will not have the same decay rate.
But here we are, but in the Doney theorem, we take m to be very large. I mean, not of Sn is centered, so we do not take m to be of order square root n. We take m to be, that's right.
m of order epsilon n.
Yes.
Then the left-hand side, so your the
This one.
probability that Sn is m will decay exponentially, right? But the probability that x1 is m might decay much faster.
But I thought you had the extra assumption of the Doney's theorem.
Yes, in Doney's theorem, we assume that the probability that x1 is equal to something is polynomial. So I'm not sure it decays. So I'm not. So I'm not sure it decays exponentially fast. It's actually this assumption in some way tells you that this does not decay exponentially fast, which is the reason why you have this one big jump which appears. I think. But okay, I'll check it and okay. Sorry for that. Okay. Are there other questions? So if not now, the one big jump principle. So we assume as before that probability that x1 is equal to n is of order L of n divided by n to some power. And now we denote by x n n minus 1 the vector constructed from the first n jumps, the jumps obtained by removing the maximal jump. And if there are many jumps which are equal, you take the first one. We have a random walk which makes n steps, and you remove the maximal jump. This gives you this vector. Then we have the following result, theorem. Due to Armendariz and Loulakis in 2011. It tells you that under the conditioning that Sn is very high, when you remove the biggest jump, asymptotically you just see n minus 1 IID random variable. Z. Assume, let xn be such that the inferior limit of xn over n is positive, so xn grows at least like n. Then the supremum over all events which involve n minus 1 jumps of the probability that the n minus 1 jumps do something once you have removed the maximal jump is roughly the same as for the unconditioned random walk. Where x n minus 1 is just a vector of n minus 1 IID jumps. So this is a very strong result because it's a result in total variation. It really tells you that asymptotically, once you remove the biggest jump under this conditioning, what you see are n minus 1 IID random variables. So, and conversely, it tells you that if you want to simulate a random walk under the conditioning Sn equal xn, what you should do is just sample n minus 1 IID random variables and put somewhere a big jump in any position uniformly. And the big jump should be chosen so that the sum of all the jumps is xn. It's a very powerful result. And I'll give you maybe the idea of the proof. And the proof is very short and really relies on the local estimate. And so it's a bit magical because here it's a very strong result for the trajectory of the random walk in total variation. And the only tool you use is the local estimate on probabilities. Idea of proof. So we fix a positive k and let Gn of k be the event after n minus 1 steps we are not too high, and the maximum jump of the first n minus 1 steps is less than xn minus kbn. So why we introduce this event? Because if we look at the probability that once I remove the maximum jump on the event that Sn is equal to xn, this is bounded from below from the probability by the probability that xn minus 1 belongs to A, Sn equals to xn, and the event gn of k is realized. So why? What happens when this event is realized? I'm saying that when this event is realized, the maximum jump occurs in the last position. So this vector obtained by removing the last jump is just xn minus 1. Why? Because this event tells you that Sn minus 1 is not that large. The maximal jump among the first n minus 1 jumps is smaller than xn minus kbn. So on this event, what does the last jump do? It goes from somewhere smaller than kbn to xn. So when this event is realized, the last jump is greater than xn minus kbn. And since the first n minus jumps are smaller, it means that when this event is realized, the largest jump is the last one. So actually this probability is exactly the probability this probability is equal to this probability, and then I just forget this event, and you get this. Here I have done this reasoning for the last jump, but you can do this reasoning for any of the n jumps. So you get a factor n here. Okay, so what does this mean? This is equal to n, probability that xn minus 1 belongs to A. Gn of k is realized, and the probability and the last jump brings Sn minus 1 to xn. And before the last jump, the walk is in the interval minus kbn, and after the jump, it is equal to xn. So what does the last jump do? It has to be equal to xn minus something with a small kn, with kn smaller than kbn. But this thing is asymptotic to probability that x1 is equal to xn. We have this uniform estimate for kn small. Xn is of order n at least. Kn is smaller than kbn. Bn is a lot smaller than n. So we have this estimate because of our assumption. Okay, and this is asymptotic to 1 over n probability that Sn is equal to xn by the local estimate. So conclusion, probability that xn minus 1 n belongs to A, Sn is equal to xn is at least 1 minus epsilon n with epsilon n tending to 0. And what do I gather here? I gather here I have this n which comes from here, and I have the epsilon n which tends to 0 from this asymptotic estimate, and then I put 1 over n, probability that Sn is equal to xn, probability that the first n jumps are in A, and the event Gn of k is realized. So the n's cancel. I can remove this by conditioning. And finally, we get probability that once we remove the largest jump under this conditioning minus probability that xn minus 1 belongs to A. I have subtracted this probability from both sides. Then you see that this is bounded from below by this quantity. And here is the trick. Here's the but here you have only a lower bound, and if we want to show that this is small, we need a lower bound and an upper bound. And here, when we started doing lower bounds, it was this is the easy part, because we say if something holds, then this holds. But here the idea, and this is really thanks to the fact that we're working with any event A, idea is to take, in this inequality, the complement of A instead of A. And this gives you immediately the other inequality. So you have actually a control in absolute value. And it remains, epsilon n goes to 0, and it remains to check that you can choose k sufficiently large so that the probability of the event Gn of k is small for large n. And this is not difficult because we chose Gn of k to be a typical event for the non-conditioned random walk. But what is, sorry, I'm going too fast. Here I subtract this probability, so I'm using the complement. So I should put complements here. Sorry, going too fast. Okay, the idea is to this you write it as probability that xn minus 1 is in A minus probability x minus 1 belongs to A and Gn of k does not hold. So you replace this with this. This term gives you this, and this comes from this. Okay, but the probability that Gn of k, there were two things in Gn of k. The location of s minus 1 is small. And the third thing was that the maximum was not too large. Okay, and now this converges as n goes to infinity to the probability that the random variable y, which appears in the extension of the central limit theorem, is greater than k. And indeed, this goes to 0 as k goes to infinity because y is a random variable. And this goes to 0 as n goes to infinity because n times the probability that x1 is greater than x minus k bn. This is of order n to xn minus k bn to the power beta, with beta greater than 1. And xn is at least n. So you see that this goes to 0 as n goes to infinity. So, yeah. Okay, maybe it was a bit technical, but okay, I wanted to maybe try to convey the main ideas. If you're interested in the proof, you can look at the lecture notes. So sorry for the this, which seems weird. So I'll tell you about this. Yeah. Yes.
It's for C strictly larger than 1, actually.
Okay. You okay.
So you cannot use it to
Okay. Yeah.
look at gems that are smaller than the natural scale.
Yeah. Okay.
So it is to be used when x is, goes to infinity and c is a bit larger than
Okay. Yeah. So I should check in the proof where we should be careful about c being greater than 0 or 1. Okay. Thank you. Yes. Okay. Okay, and final comment. So here maybe it was a bit technical, but there was really two ideas. The first idea is you have a local, an estimate on a local probability. This one, the first ingredient, and the second ingredient was to introduce an event Gn of k, which was typical. And this was actually the main idea. We showed that Gn of k was typical for the non-conditioned probability. We did not show that it was typical for the conditioned probability. So what happens here is that to understand to show actually that a sort of one big jump happens under this conditioned probability, you show that the one big jump principle sort of holds for the non-conditioned probability, which is a lot easier to manipulate because you are non-conditioned. And since you're working with probabilities, this gives you information that you cannot have a loss of probability. So maybe what I'm trying to say, okay, maybe I'll try to maybe formalize things a bit. Okay, so we want to show, so this is a bit hand-wavy, mu n is, roughly speaking, mu n tilde. Mu n is complicated. This is not complicated. The idea is to find an event En typical for mu tilde n such that on the event En, mu n and mu n tilde are the same. And this implies that globally mu n is roughly the same as mu n tilde. And the thing is that you do not have to check that En is typical for the complicated measure, okay? This is actually what is happening here, and this is an idea which can be applied in more general contexts. And also I have updated the lecture notes with the solutions of the exercises, so you can have a look, and if you find typos or mistakes, don't hesitate to send me an email or to tell me. So thank you for your attention.
Are there questions for Igor? Seems everybody is hungry, so let's stop this morning session, and thanks to all the speakers.